Donc, bonjour et bienvenue à toutes et à tous. Je suis Laurent Pécastin, membre du comité opérationnel de SUPPA. Et avant de passer à la conférence de M. Lobinski à proprement parler, quelques informations sur E2SUPPA et en particulier sur les appels à projets qui sont actuellement ouverts. Donc le premier qui se clôt demain, c'est un appel à projet qui a été lancé pour des nouveaux partenariats, où les nouveaux partenariats sont privilégiés avec des effets de levier espérés. Donc l'idée est qu'un partenaire privé ou un EPIC puisse cofinancer une bourse de thèse, un contrat de postdoc ou un contrat de recherche. Donc deadline demain soir à minuit, il ne faut plus tarder. En ce qui concerne l'Académie des talents, la nouvelle vague pour l'Académie des talents, deadline le 26 avril, certains parmi vous sont membres de l'Académie des talents. Et donc la nouvelle vague, donc pour attirer des étudiants de qualité ou pour retenir nos meilleurs étudiants, des bourses sont offertes aux étudiants de licence, de Master 1 et de Master 2. Également un appel à projet sur les bourses d'innovation pédagogique. Donc là, l'idée c'est de permettre la mise en œuvre de techniques ou de techniques pédagogiques innovantes. Et enfin, deux appels à projets concernant les mobilités à l'international, donc pour mettre en œuvre des projets de recherche internationaux collaboratifs avec, si possible, des universités qui ont été qualifiées comme cibles pour le projet E2S. Donc il s'agit de mobilité pour les doctorants qui ont soutenu en 2018 ou qui vont soutenir en 2019. Pardon, autant pour moi. Pour les doctorants qui n'ont pas encore soutenu, bien sûr, autant pour moi. Et donc pour leur permettre une mobilité de 3 mois au minimum. Donc là, l'idée c'est de leur offrir les moyens matériels d'effectuer cette mobilité. Et donc, pardon, c'était pour les post-doctorants, il faut avoir soutenu en 2018 ou soutenir en 2019. Et l'idée là, c'est d'offrir un salaire d'une année à un étudiant fraîchement diplômé pour aller dans un laboratoire hôte et mener à bien des recherches collaboratives. Je cite également deux autres événements à venir. Le premier, c'est que 2SUPP organise un séminaire thématisé énergie-environnement sur la création d'entreprises qui aura lieu du 22 au 24 mai à Cabreton. Il reste encore 1 ou 2 places de disponibles pour les personnes désireuses de s'inscrire. Donc l'idée est de travailler sur un projet de création ou de transfert de technologie vers une entreprise. Et à propos de transfert de technologie, il existe également un appel à projet qui est ouvert au fil de l'eau, qui permet de financer des projets de prématuration, de maturation ou de post-maturation de projets. Pour terminer, la prochaine conférence aura lieu le jeudi 9 mai. Elle sera donnée par Madame Isabelle Moretti, qui est récemment recrutée à l'UPPA et qui est une ancienne directrice de recherche de chez Engie. Donc elle nous parlera de l'hydrogène naturel, curiosité géologique ou futur or noir. Et cette conférence fera suite à l'Assemblée Générale de 2SUPPA, à laquelle vous êtes tous invités, qui aura lieu ce même jour, donc le jeudi 9 mai à 14 h. Je vais maintenant passer la parole à M. Laurent Borde, le directeur du collège STIC, pour introduire M. Lobinski.
Bonjour à tous. Donc j'ai le plaisir de vous présenter Richard. Vous le savez probablement tous ici. Richard, c'est le directeur d'une UMR de l'université, la plus grosse des UMR de l'UPPA, entre l'UPPA et le CNRS, l'IPREM. Quelques éléments du parcours de Richard, c'est important, je pense, parce qu'il y a beaucoup de doctorants dans la salle, et puis ça vous donne un petit peu une idée de ce que vous pouvez faire pour faire une jolie carrière. Donc Richard, il a été formé, sa formation initiale, c'est à l'école polytechnique de Varsovie. Vous reconnaîtrez peut-être un petit accent polonais lorsqu'il parlera, mais tu vas parler anglais, je crois, c'est ça?
Oui, mais l'accent polonais est toujours là.
En anglais, ça marche aussi. Donc il a obtenu son doctorat en 89 à cette école polytechnique de Varsovie. Ensuite, il est parti 1 an à Dortmund, en Allemagne. Et ensuite, a passé 3 ans à Anvers, donc en Belgique. Et il a été recruté en 1994 comme chargé de recherche CNRS à Bordeaux. Tu étais dans un laboratoire bordelais, enfin au CNRS dans un laboratoire.
Oui.
En chimie à Bordeaux, et pendant 3 ans, tu es resté à Bordeaux avant de venir rejoindre l'université de Pau et des Pays de la Dour. À l'époque, l'IPREM n'existait pas encore, mais ça allait venir. Et donc, il a été nommé directeur de recherche en 2000. Donc, ça a été une carrière plutôt fulgurante. Comme tous les chercheurs de haut niveau, on peut le voir à travers son parcours, Richard a fait des séjours dans des universités étrangères. Moi, j'ai cité l'Allemagne, il y a eu le Japon aussi, la Pologne, puisque tu as gardé des liens assez privilégiés. Je crois que tu es professeur associé de l'école polytechnique de Varsovie où tu as été formé. Voilà. Et donc voilà, un joli parcours académique. Pour les compétences, alors je suis assez mal placé pour parler, je suis mathématicien moi, donc pour parler de la chimie. Donc j'ai été voir, je le disais tout à l'heure à Richard, j'ai été voir sur sa page web, à compétences, j'ai trouvé chimie analytique, voilà, 2 mots, mais qui résument assez bien, je pense, ce qu'a fait Richard. Plus sérieusement, Richard a eu la médaille d'argent du CNRS il y a quelques années, et ça a été l'un des pionniers dans la mise au point de méthodes analytiques pour permettre l'identification et la détermination de formes chimiques dans l'environnement et dans les systèmes biologiques. Donc je crois qu'on appelle ça la métallomique. C'est ce qui lui a valu cette médaille d'argent du CNRS, qui est quand même une reconnaissance extrêmement importante pour l'activité de recherche. Alors, je ne peux pas en dire beaucoup plus, sinon, voilà, que Richard a un parcours brillant, que c'est un des chercheurs qui nous a aidé au sein de l'université à mettre en avant ces talents dont on avait besoin pour réussir ce projet E2S UPPA. Je pense que ça a beaucoup compté dans la perception de la qualité de la recherche qui est effectuée à Pau. Et puis maintenant, j'ai le plaisir de te laisser la parole pour raconter des vraies choses scientifiques.
Merci beaucoup Laurent. J'ai mon micro à moi. Je juste change de présentation. Là voilà. Donc, effectivement, ça fait 22 ans depuis que je suis arrivé à Pau. Et c'est ma première conférence à l'université. D'autant l'honneur est plus grand. Well, I have been asked to give this lecture in English, so I will switch to English from now on. As a chemist, I will start with the fundamentals of the periodic table of elements. As you know, the different elements are organized and displayed in the periodic table. Devised by Russian chemist Dmitry Mendeleev 150 years ago, the periodic table tells us a lot about the chemical reactivity of elements, how easily they combine and bond with each other, producing chemical species. And the periodic table of elements is clearly one of the most important and influential achievements in modern science. And no wonder that the United Nations declared the year 2019 as the International Year of the Periodic Table of Chemical Elements. One of the most spectacular theories based on the periodic table is the theory of a German scientist, Ida Noddack, the theory on the overall occurrence of the chemical elements. In brief, as early as the 30s, Ida Noddack postulated that every chemical element can be found in any mineral ore, and then she extrapolated these hypotheses to living organisms. Well, this means that elements missing in material are ones that were not sufficiently looked for. And this also means that there is a minimal concentration at which a given element is present in any mineral, and this concentration is referred to as universal concentration. So in brief, anything is present in everything and everywhere. The universal abundance of matter. But Ida Noddack's theory addressed naturally occurring elements only. However, over the last century, the human mining activities and the worldwide use of certain substances, and finally nuclear testing and nuclear power plant accidents released into the environment considerable amounts of anthropogenic chemical elements, resulting what is referred to as the global fallout. So the person who first realized that any compound produced by man will eventually be found at any place on the earth was Claude Patterson at the Caltech. Patterson drew public attention to the problem of increased lead levels in the environment and the food chain. So this lead would be originating from the massive use of gasoline to which tetraethyl lead was added as an anti-knock agent. Patterson was also the first to realize the necessity of analytical measurements in clean rooms. And he can be considered as the pioneer of ultra-trace analysis. He also opened the way to studies of the global fallout in polar, so Antarctic and Greenland ice cores. So any substance released by man wherever on Earth would find its way to any, however remote, environment. Avoiding contamination at any level of the analytical is of critical importance. So imagine the trace analysis of metals in human blood. So blood is taken in by a syringe. Syringe needle is made of stainless steel containing cobalt, nickel, molybdenum, manganese, and chromium, and maybe other elements. And imagine that if you take blood from a patient, you get much more manganese, chromium, nickel, cobalt, and molybdenum from the needle than from the patient. So if you want to determine these elements in blood at the levels they are there, and these levels are trace levels or ultra-trace levels, then you have to avoid the contamination. So you have to use a plastic needle, and you have to use clean room conditions. So Claude Patterson is constructed the first clean room for analytical chemistry. I am talking about Claude Patterson because he had a brilliant postdoc, Claude Bootrom, who later became director of the Laboratory of Glaciology and Geophysics in Grenoble. And I'm mentioning Claude because this is his project that brought me to the field of ultra-trace analysis in the early 90s, and which brought me ultimately to France. So it really changed my life. The challenge was to identify in Greenland and Antarctic snow the specific signature of lead added to gasoline, which was expected to be present largely below picogram level. Picogram is 10 minus 12. But actually it turned out to be present at femtogram levels. So it's 10 to minus 15 grams. So this requires contamination control, and there are here some pictures of sampling consisting of isolating the internal part of the cortical The outer part was already contaminated by environmental air. And this was done in the first laboratory in France, which was in Grenoble. It was founded by Claude Bootrom. So the articles mentioned for the first time in analytical chemistry femtogram detection limits, which corresponds well to finding a particle of a nanometer size somewhere between. So what is the femtogram? Well, it's basically a probability of finding a particle of a nanometer size lost somewhere between the Earth and Mars. So these findings were possible by a novel approach to analytical chemistry, development of analytical techniques introducing plasmas for the detection of ultratrace elements, and well, I will talk about it later. So what is ultratrace analysis? So what I want to say at this point is the first lesson from Ida Nodak's teachings, which was the origin of the concept of what we call now ultratrace analysis. So if there are elements missing in the material, it means that these elements are those that were not sufficiently looked for. So, and the power of analytical techniques is driving us every year closer to allowing the counting of individual atoms of even most exotic elements in the periodic table. So nanomole, picomole, femtomole, attomole, zeptomole, yoctomole. Well, yoctomole is probably for the next generation. So the second point I want to make, talking about Ida Nodak's teachings, is that we have entered into an era of oblivion. So oblivion means a state of being unaware or unconscious of the presence of chemical elements around us. So let's look at this graph. Showing how the concentration of radioactive cesium changed over the years. There is a peak in the early 60s, well, of course, nuclear testing. There is, you can also recognize a peak in 86, so it's the Chernobyl's signature. But it's not the most interesting thing in this picture. The most interesting thing in this picture is the sample where this radioactive cesium was found. And the sample is a sample that we consume every day. It's wine. And so you can say that we drink radioactive cesium every day, which is technically speaking true and would make a headline in the media. And staying with wine and media, it may be worth to think for a moment of the perception of an average citizen about the meaning of analytical results, and the understanding of ultratrace analysis gives here a perfect opportunity. So the vintage wines are an excellent archive of environmental pollution. Well, they are well dated. Well, if you have a bottle, you see the vintage, and they are well preserved. Well, the bottle is closed, so there is no contamination. So for amusement, some time ago, we tested with Claude and Pierre-Louis Tessèdre, who is now a professor at Bordeaux University, a series of vintages of Châteauneuf-du-Pape. So it's a vineyard which is located at the junction of two busy motorways, A7 and A9. And what we wanted actually to say is whether we recover traces of leaded gasoline fallout in the wine itself. So, and indeed, as you can see, well, there is a peak in the concentration of organic lead in wine in 78. And again, well, maybe it's not the most interesting thing about this work. What is interesting is that this work obtained much more attention than it really merited, because an amalgam was made by journalists between lead and toxicity, demonstrating the complete misunderstanding of what the meaning of the presence of ultra-trace of different substances in food was. So the funniest conclusion, if it's big enough to read in the screen, was made by the journal Le Monde, insinuating that by this study I was supporting the movement against the construction of a motorway in the Loire Valley. I never heard about this before, and I really don't know how could they come up with this. So I really prefer the comment of the Guardian. Well, this was a very enjoyable research. So I got one opportunity once in my lifetime to taste all the vintages of Chateauneuf du Pape, starting in 28 and finishing in 95. So coming back to Ida Noddack's theory. Actually, not only every element can be found everywhere, but also each of its isotopes. So I remind those who skipped classes in chemistry that isotopes are atoms with different number of neutrons, and that isotopes are undistinguishable chemically. So, with the exception of monoisotopic elements such as arsenic, as you can see, which have one isotope, and those which do not have a stable isotope, so artificial radioactive elements such as the americium that you can see here, all the other elements have at least two or more stable isotopes. So why we talk about isotopes here? Well, because they can be useful. So lead, for instance, has 4 stable isotopes, of which the concentrations vary as a function of the age of the rock, and it means as a function of the geographical region. So on the basis of the isotope ratio, we are able to tell the geographic origin of wine. So it works even better for strontium, where the soil composition varies from one vineyard to the other and is reflected in the wine composition. So these studies were carried 20 years ago by a very clever student of mine, Mireille Barbaste. Even if technically she didn't do the work here, because we were not as well equipped as we are here. Well, actually, the studies were done in Oxford and at Oxford University, and the Geological Survey of Israel in Jerusalem, but she defended her thesis here. So for those of you who have not defended the thesis yet, go somewhere, carry out some successful experiments, come back to Po, defend the thesis here. The doctoral school will be proud of you. But let's go to the Ida Noddack's theory again, and the title of this lecture, In Quest for Trace Elements in Biology. So when the Earth was formed, all elements were present and their distribution equaled their universal concentrations. However, the biological organisms changed this distribution of elements and changed the distribution of the isotopes in the process of evolution. So in order to develop, the organisms started to enrich some elements they needed and started to avoid the others they didn't need. So in this way, we've got the distribution of chemical elements in a biological sample in life. But the question is, what were these mechanisms of enrichment and avoidance, and how these mechanisms can be studied. So here we arrive at the concept of the biological periodic table, or of the periodic table of biological elements. The concept that was introduced by the late Robert Williams at Oxford, and later developed by Wolfgang Maret, now at King's College London. So elements are universally used in nature, and their uses can be diverse. And indeed, if you look at this, it's clear that life would not be possible without hydrogen and oxygen, which are components of water, neither without carbon, nitrogen, and sulfur, which are, well, it doesn't work, so if somebody can help me with the pointer, I would be grateful. Si quelqu'un peut m'aider avec le pointer, donc ce serait pas mal. Well, if not, well, then life would not be possible without carbon, nitrogen, sulfur, which are components of essential amino acids, nor phosphorus, which is a component of DNA. And these elements are called major essential chemical elements, essential for life. But let's add to it minor essential elements. So sodium, maintaining osmosis. Sodium, as you know, is a main cation in blood, and it's compensated by an essential element, which is chlorine. The charge of sodium is compensated. Potassium, both sodium and potassium are involved in sodium-potassium pump. Magnesium, component of chlorophyll. Iron, used in hemoglobin. Calcium, used as a component of bone matrix. So if we add all these major and minor essential elements, we come to about 100%. But if we want to be accurate in our calculations, we will realize that there remains a very tiny fraction of trace and ultra-trace elements that are not less essential, and these are these elements that I would like to discuss today. So, manganese, cobalt, nickel, copper, zinc. Why they are essential? They are coordination centers of vital enzymes. Well, there are thousands of enzymes, of which zinc is the coordination center. And well, if you add to it molybdenum, we can add to these elements, well, boron, well, it's slightly different. But iodine, well, it's interesting. It's a component of thyroxine, so we need iodine to live. So these are essential trace elements because the concentrations do not reach a small fraction of 1%. Well, I have not finished. There are some other elements. There are two of them which are very characteristic. It's chromium and selenium. I would like to discuss them because, well, selenium is definitely essential. It's a component of glutathione peroxidase. But try to explain that selenium is essential to inhabitants of California's San Joaquin Valley. Well, these inhabitants have been fighting for decades against selenium pollution, because whether selenium is essential or toxic, it depends on the concentration, and it depends on the chemical species. It depends on the chemical form. And it's the same with chromium. You've got, it's called chromate or chromium-6, which is extremely carcinogenic, but you've got also chromium, which is an essential element for life, and it is sold in a drugstore as a food supplement. So there are plenty of other useful elements to a point that a medicinal periodic table was drafted by Peter Sadler, a professor at Warwick University. And we can use elements as drugs. Well, anti-cancer drugs, cisplatin, contrast agents, well, gadolinium. Well, this is a very rare element, but It's used as a contrast agent for magnetic resonance in diagnostics. Even gold can, in the form of some compounds, can have anti-cancer properties. So metals can be useful, but there's also a dark side of metals. These are notoriously toxic trace elements. Well, mercury, lead, cadmium, bismuth. Well, that's if you just hear about lead or mercury. Well, it's obviously toxic. There's no way. The industrialization is progressing. So new technologies use more and more exotic elements. So platinum, palladium in catalysts, silver nanoparticles are everywhere. Neodymium, neodymium. Who ever heard about neodymium 10 years ago? And now you've got a lot of neodymium in each of the smartphones. It's a very essential element for new technologies. Titanium, it's ubiquitously present in cosmetics. But is it really non-toxic? So what is the impact on the environment of all these technologically critical elements which are now present, as I said, everywhere on the Earth at trace concentrations, and their concentrations are increasing. So at this point, there's a take-home message. Well, first, that chemical elements are ubiquitous in biology at different concentration levels and are universally used by man and nature. So they are either essential, they have either essential life functions, or they can be used for therapy. Living organisms have developed a number of mechanisms to protect themselves from toxic metals. And probably the most important thing is that the role of metals cannot be understood without understanding their speciation. Indeed, it's not the element itself that is really important, but it's a chemical species. So it's not the platinum that has anti-cancer activity, but it's its chemical forms, its platin, of which the invention has brought billions of dollars in revenue. It's not cobalt that is essential, it's its specific chemical form, methylcobalamin. It's not arsenic that is toxic, it's its specific inorganic arsenic form. So when you have a good seafood meal, you consume more arsenic than the lethal dose, actually, on 1 or 2 evenings. But before your lobster or fish or oyster was killed to be eaten, it managed to have rendered this arsenic inoffensive. So be thankful to the lobster you eat, because otherwise you would have taken in inorganic arsenic. And the lobster did it for you, and it metabolized it. So be thankful to your lobster. So the concept of elemental speciation as an interdisciplinary area of capital importance to understand the fate and toxicity of trace metals, well, is recognized in this report that I'm inviting especially PhD students in analytical chemistry to read. It's 20 years old, and it was published by the International Union of Pure and Applied Chemistry, IUPAC. The chemistry of structures and functions of metal ion complexes with biological ligands, bioinorganic chemistry as we call it, has been extensively studied. It's even taught at some universities as an independent matter. It has been a subject of several textbooks. However, neither a metal or a bioligand, well, bioligand is an active, a reactive compound which is present in the biological environment. So it forms coordination, it coordinates metals, or metals are coordinated by ligands, if you prefer this way. So all the elements and many bioligands are present together, and many interact. And understanding the interaction in vitro, so if you just put them in a test tube, this is not enough. It's not an evidence of their interaction in vivo. So because the function of the metal is conferred by its biological context. So consequently, the role of different components of a biological system can only be understood if they are considered together. So this is what we call systems approaches. So what is a systems approach? A systems approach is a holistic in contrast to a reductionist approach to biological research, which answers the question how the collective information of all the components in a system give rise to the physiology and pathology of the system. So we have entered here into the era of omics. Hans Winkler, well, 100 years ago, so probably you have never heard about him, but he was a German botanist who coined the term genome. And he coined this term genome as a combination of gene and chromosome. So it was a linguistic creation without any real scientific significance. And Winkler couldn't anticipate the success of this suffix "om," and the success, well, is due to the work of American bioinformaticians in the 90s who coined the term genomics in the mid-90s. So, and as the term was becoming famous, well, people thought that well, maybe Greeks had anticipated it because apparently, well, I tried to check it, but it's very difficult to check it. Om should stem for the Greek for all, every, whole, or complete. So if you are Greeks in the audience, please confirm or infirm this. Well, in Sanskrit, this I checked and it's true. Om means fullness, completeness, as in divinity. It encompasses the entire universe in its unlimitedness. And this is what omics is about. So genomics with the Human Genome Project, which led us to the knowledge of our genome, but then scientists realized it's not the genes, it's the gene products, so proteins. So let's look for proteins, let's look for proteins in the globality. So here it's how proteomics was born. Well, but then proteins, when they act, well, they produce metabolites. Oh, metabolites are important. So let's talk about the metabolome. So we've got a human metabolome project. So we've got many oms. So it's not the last one. I will talk about other oms. But well, the question is obviously what is the place of metals in this context, because as I said, that evolution modified the distribution of metals. So the variety of paths which individual elements follow in any organism has created a specific element distribution. And this specific element distribution we call metalome. So that's the definition. I will come to it in a moment. Well, the concentrations of individual elements are controlled by the physiology and biochemistry of an organism and ultimately by the genome. So, and metal, because as they are coordinated, as they serve as coordination center, they give functions to metabolites and to proteins. And there is a link between the genes and metals, because genetic codes for the incorporation of several metals have been identified, and metalloproteins and metal binding sites can be predicted on the basis of the genome. So here, this brings us to a global study of metals and their interactions in biology. Metalomics. The origins of Metalomics go back to a meeting held in Japan in 2002, where a dozen of invited speakers coming back from a conference dinner entered into a discussion on the global view of metal biomolecule interactions. So I think we had all consumed too much sake, but it was very creative. As Professor Hiroki Haraguchi, well, whom you see here, well, he took a piece of napkin and he wrote something like that. Well, anyhow, even Japanese can read it because, it's in Japanese, but this is the essence of metalomics. It means that the metalome is an essential component of each and every biological system. So the metalomics movement gained momentum, and in 2008 we had a meeting at the University of Cincinnati, where we managed to convince the British Royal Chemical Society to launch a journal dedicated specifically to this field. Well, and this journal 10 years ago still exists, and its impact factor is even climbing, so it's a good thing. Well, there have been several books published since then, and what is important is that there was a metalomics community created, assembling every 2 years over 300 scientists, and metalomics was well recognized by the International Union of Pure and Applied Chemistry as a concept with a specific meaning in chemistry. So it's the last 10 years of our work here in Po in a very broad international context. But what is actually metalomics? Metalomics is a synergy of two conceptual approaches. So one is a reductionist approach. Reductionist approach, well, we can either predict or determine parts of the system, so metal ions, ligands, or species, well, and create lists of these species. Well, that's the metalome. We can characterize a metalome of a biological system. But there is more, and I think that's the interesting part, and it's a holistic approach. So it's assembling these parts to functional units to learn how metal ions work in the system. So why these metals interact with the ligands, and what function it brings to a biological system. So a reductionist approach, where is pure advanced analytical chemistry. What analysts do? Analysts, analytical chemists look for tiniest ultratrace components of a system. So which are these components? These are concentrations of the elements. These are precise isotope ratios. These are species present, so chemical speciation. We can go beyond the chemical speciation, so we can focus on the on the conformation and on the stereoisomers present. And it's the question of localization, where these metals, these species are present in a tissue or in a cell or in a subcellular compartment. So how to do it? Well, a cell is a complex environment. There are a lot of things in a cell. And the problem is also that the cell is very small. So we look for picograms in nanoliters or picoliters. Or actually we should look for attograms in picoliters. So there is a lot of, plenty of space for the technological improvement, for the development of more and more sensitive methods in analytical chemistry. And the only technique capable of seeing individual atoms, isotopes, molecules at such low levels is mass spectrometry. Well, You can look at mass spectrometry as nothing else than a technique of separating and counting ions. So it results in what we call a mass spectrum. Well, a mass spectrum, you've got x-axis, which is the measure of identity. So here is a mass spectrum for bromine. So you see there are 2 bromine isotopes, but you've got also bromine molecular clusters. So it's the measure of identity of a bromine species in a sample. And y-axis, which is the measure of intensity. So in order to arrive at such a mass spectrum, you have to form ions. Forming ions is removing electrons or adding protons. You have to weigh ions. Weighing ions is sorting them in a mass analyzer according to the mass, or more precisely to the mass to charge ratio, and you have to count them. So the principle is extremely simple. So the first question is, of course, how to obtain ions. How to obtain ions from isotopes. Any matter can be decomposed into isotopes and at extremely high temperature. So let's say at 10,000 Kelvin, no matter which molecule you have, at 10,000 Kelvin, you will have only isotopes out of this molecule. So how to obtain such a high temperature? By creating a plasma, ionized gas moving rapidly in a magnetic field, and any molecule entering this magnetic field, this high temperature, will be converted into elemental ions. And the most common plasma in the laboratory is what, well, people who are at IPREM have heard many times, and maybe also others, ICP, inductively coupled plasma. Well, but it's a technical detail, and I was told to keep this presentation not too technical. So let's come to the essentials. So what we get actually is a mass spectrum, or we can call it elemental concentration fingerprint. So it means each sample, each piece of matter is characterized by this elemental concentration fingerprint. And we can do it down to the femtogram level, or below the femtogram level. What is green in green here? Well, these are elements that can be measured, can be detected below 1 femtogram level. What is in yellow? These are elements which can be detected at 1 femtogram level. As you can see, it covers well, 80% or 90% of the periodic table. And my favorite example here is the plutonium signal in urine, which indicates an absolute detection limit of 6 attogram. Well, 6 attograms. So its attogram is 1,000 times less than 1 femtogram. So, well, you see, this is 50 attogram of plutonium. This is quite a big peak. And for those of you who have a background in analytical chemistry, this is a calibration curve, and the upper calibration point of this curve is 1 femtogram. So it's probably the only, well, it was the only, when we published it 10 years ago, calibration curve with the upper calibration point of 1 femtogram. So we can go really very, very low with the modern technology. So what can be the purpose of obtaining such an elemental concentration fingerprint? Or the purpose is to correlate it with something, with any parameter. Well, this any parameter can be, well, geographical origin of food. This can be medical history of a patient. Or it can be, as in the illustrated example, a collection of genetic mutants of a plant varying by 1 gene only. So we can correlate genes and enrichment or impoverishment in any metal. So you've got the metals here and intensity for each of the 4,000 mutants of this plant. And this is this correlation between the genome of an organism and this elemental concentration fingerprint is a fantastic, excellent starting point to study the molecular mechanisms of the role of trace elements in biology. However, metals are present as species, so at 10,000 degree, we lose the information. Molecular information is lost. So the question is, how can we preserve this molecular information? So we need to produce ions from biological ligands. And the problem how to do it was solved in the end of the last century by John Fenn and Koichi Tanaka, who invented the ways to produce ions from big biological molecules when they got a Nobel Prize for it. And these two techniques are electrospray, and so it's the formation of ions from molecules by pushing them through a capillary maintained at a high electric field and laser desorption ionization that developed later to what is called amaldi. So, well, here is a picture of Koichi Tanaka, whom we had the honor to host in Po 10 years ago. So electrospray and amaldi turned out to be fundamental for the development of analytical proteomics and metabolomics. So we are capable now of detecting, identifying, and quantifying thousands of proteins and thousands of metabolites in a single analytical run during, say, a couple of hours. Well, of course, it produces colossal amounts of data which have to be treated. Well, that's true, we can do it for proteins, metabolites, but the question is whether we can identify metal species, so the complexes, the chemical creations, using at these trace levels. Well, and the answer is, well, it's very difficult, because these canonical proteomics and metabolomics approaches well, work very well, but above the levels at which these trace and ultra-trace concentrations of metals are present. Well, the second point is that metal complexes are ionized not as readily as ligands are, well, they are not very concentrated, they are not well ionized, so they are suppressed by everything else in the sample. So if you are small, then, well, you suffer. Consequently, almost no information can be obtained on metal species by direct analysis. And so how to do it? Well, the game changer in the biological speciation analysis was the introduction of coupled techniques with dual detection. Well, coupled means that you've got a separation technique, chromatography, electrophoresis. Well, you separate the molecules, and then you detect them. You detect them as to the metal, and you detect them down to this attogram level, that femtogram or attogram levels that I discussed by inductively coupled plasma mass spectrometry. And the fact that you separate the species eliminates the interferences, eliminates the concomitant species, and eliminates the matrix in electrospray mass spectrometry. So we convert the molecular information to ICP-MS. This is the technique that works at 10,000 kelvins. And in the same time, we managed to alleviate the problem of signal suppression by a concomitant species. And again, if if you work in the field of analytical chemistry, it may be worth to read this primer published by the Royal Society of Chemistry. So, although rudimentary, in the beginning now, well, these techniques have developed into a powerful analytical tool. As you can see here, the developments of analytical methodology allow an experimental workflow in which a drop of biological liquid can be screened for the presence of metal species. So every fraction of a second, a full range mass spectrum is acquired at a 500,000 resolution, producing millions of experimental points within one separation run. And then it's mathematics, actually, how to extract this information. Somewhere in the midst of these millions of experimental points, there are signals, there are signatures of ions, of metal-containing molecules, which have to be unambiguously identified by advanced gas phase mass fragmentation, mass spectrometry, and that have to be, say, validated that they are real and they do not come from artifacts. And there is a reward for that, so that's a work of a PhD student, Paulina Fliss, who had a position in Nottingham in England now. It's a validated analysis for a large-scale speciation analysis in plant sub. So you've got plenty of elements, plenty of ligands, plenty of species, and this is possible because of the advances in the development of analytical methods. So we can add another dimension to speciation analysis beyond the molecular mass. And this dimension is the study of the mobility of different conformers, different isomers of metal-containing molecules in the gas phase. So what was a single peak before, a single molecular mass, it's becoming now several peaks because the same molecule can be present in different conformations. And what is interesting that these conformations are stable, and these conformations may have biological meaning to be looked for. Another aspect of ultra-trace analysis is to carry it out with spatial resolution. So not in the bulk of the sample, but go to micrometers, to sub-micrometers, to nanometers, and carry out this elemental concentration pattern analysis using, say, laser ablation with this 10 micrometer resolution, multi-mass spectrometry with 50 micron resolution. But you can get better spatial resolution by going to micro XRF using synchrotron radiation, or what is called nanosecondary ion mass spectrometry. But remember that the better your spatial resolution, the less matter, the less ions you produce. So the more difficult is to detect them, the more difficult is to produce meaningful analytical information. So the last part is how to move from this reductionist, purely analytical chemistry approach to the holistic approach. So establishing the list of the parts of the system is only a starting point of scientific discovery, because the ultimate goal is to understand why nature has produced these species, what are the mechanisms involved in the trafficking of trace metals. So, well, I think that there are three steps to discovery of new molecules and their functions. Well, the first step is definitely a thorough and comprehensive observation and analysis of a system. So we have to know what is there, and I have just well explained how we can know what is there. And then advanced science starts. It's a question of a daring hypothesis. What do we think this information, how this information can be interpreted? And the last, but not least, well, is to have a bit of luck. It's to have a bit of luck that this hypothesis becomes true. And I will illustrate these 3 steps to discovery by our latest research on the role of metallophores in pathogenic bacteria, Staphylococcus aureus. Well, it's a nasty bacteria. Well, it's associated with the worst illnesses you can imagine: respiratory infections, food poisoning, whatever. Well, the question is how this bacteria survives. And this bacteria survives and develops when it gets metals from the host. And it gets these metals by synthesis of molecules which are powerful enough to attract the metal from outside. So these molecules are called metallophores because of their affinity to metals, and the bacteria acquires these metallophores by releasing acquires metals by releasing metallophores. So, well, the first step, a thorough and comprehensive observation. So it's the cartography of metal complexes in this bacteria, and if we carry out a thorough characterization of the system, we come up with a number of metal complexes, which you can see here. But what is interesting that all these metals, whether it's cobalt, copper, zinc, or nickel, they share the same ligand, and we can read it because we can weigh by mass spectrometry the metal ligand complex. And if you measure the mass accurately, then you can come up with the empiric formula. So how many atoms of each kind the molecule has. Well, that's if you have a candidate molecule, well, then you can carry out all the atmospheric, all the gas phase chemistry in a mass spectrometer to come up with a hypothesis of a formula. Well, you just need to validate the formula by custom synthesizing a molecule and comparing the physicochemical properties either by mass spectrometry or magnetic resonance. So, step 2. Well, look at this molecule. And this is what is a daring hypothesis, and this is why you need collaborations. So this molecule can be seen as a molecule composed of 3 pieces, and what is really here very interesting is that this piece in the middle, alpha amino butyric acid, is a component of a known compound. It's called nicosinamide. This is coded by an enzyme, nicosinamide synthase. If it's an enzyme, then well, it's coded by a gene. So you can associate a gene to this fragment in the middle of a protein, but it's still a hypothesis. You confirm this if you remove the gene, and if the gene is removed, the molecule is not synthesized. So it means that the hypothesis was correct. So, and if you have the gene that is associated with this piece in the middle, then by looking into the genome, you've got genes upstream and downstream. And so it means that you can make a construct. Well, this is called operon, that you've got 3 genes, and and bingo, these 3 genes all together, they synthesize the molecule. Because it's synthesized, it's expressed if these 3 genes are present together, and then it's not in the control sample. So that's it. So you've got a proof that there is a sequence coding, well, each of the genes coding for a specific enzyme, and that these 3 enzymes working together, they are able to synthesize this molecule, which is crucial for the import of essential elements for this bacteria to survive. I'm not saying that I want this bacteria to survive, because this is why we do it. We want to understand how this bacteria survives in order to cut this paths for its survival. So if you see these 3 enzymes, so the first produces the left part of the molecule to simplify the things. The second is the middle of the molecule, so our reasoning started from this middle, and the other one terminates the synthesis. So that's, well, I finished. And to conclude, just 5 points as a take-home message. So the first is trace and ultra-trace elements play a fundamental role in the chemistry of life. So any or most of life essential processes are critically dependent on an enzyme, and this enzyme often uses a metal as a coordination center. All the elements are around us. So the growing anthropogenic pressure requires the study of effects at the cellular level. So now look at technologically critical elements. That's how are they toxic and what are the mechanisms of their toxicity. Modern analytical techniques can bring information on the multi-element, isotopic and molecular composition at the cellular level and below. So we are well equipped. Yeah? And analytical chemistry is not enough, so the discovery of new functional metal trafficking molecules requires global approaches and close interdisciplinary collaborations. And for the younger generation, there is plenty of room for discoveries of functional molecules for metal removal in the environment and metal-based therapy. So we have just been starting, well, in 3 days, a hub. So it's one of the big projects of environment and solutions program going into this area. So we are well equipped. So if you want to talk about engineers operating these fabulous mass spectrometers, we've got plenty of mass spectrometers and we've got plenty of engineers in EPREM. Please come, see, discuss. Ohms matter. So if you like crossword puzzles, well, Metalom is there. The metals and metal-containing molecules in a cell or tissue. So it has entered into the public environment. Indeed, so we hosted a team of the Japanese television, NHK, and for those of you who read fluently Japanese, so this is Po University here, and this program is watched by 30 million people. Japan and China are big countries. We organized the first Franco-Japanese workshop here in Po on Metalomics. So I would like to thank Environment and Energy Solutions program for the invitation. I would like to thank all of you for your attention. And well, I leave the floor to Laurent or Xavier. Or